All right, we're going to look at limits. Limits form the basis of all work in calculus, so it's very important that we understand these. The whole chapter is devoted to it. Now we're going to look at numerical, graphical, algebraic approaches, and more. So let's, I just want to give you an idea of what a limit is. And then we'll move on there for a formal definition. Basically, we're looking at the behavior of a function. At certain points. Okay, so if I graph this function, remember x is in radians. At 0, of course, it's going to be undefined, so we have a little hole there. Right. Looks something like this. So, well, obviously, this is defined at 1, so we don't have a value there. But what we can do is we can look at the behavior of the function from the right and from the left to determine where that graph might go. Okay, what is the behavior of the function in that area? Okay. Graphically, we could say as x approaches 0, so x is coming here and here, f of x approaches 1, so it's coming here. So you can see these arrows come to 1. So this is the x value, this is the y value. Okay, we can write it mathematically like that. We can also write it as the limit as x approaches 0 of f of x equals 1. Okay, this right here is where we'll end up in our coursework. Okay. Just look at, okay, this means if I put a minus sign there, it means from the left. So I'm approaching it from the left only. I'm not including this, so we can just cover that up. All I'm looking at is this one right here. The same way we can look at from the right. Okay. Because these match, we can say that the entire limit is 1. Okay, I'll go over that a little bit more here in a minute. So this is graphical. We can also do a numerical approach. Here will come from the left, and here will come from the right. So this does take a little bit longer, but sometimes it's necessary. So basically what you're doing is you're getting closer and closer to 0 because we're approaching 0 there. Okay. On your calculator, make sure you're in radians mode here. You're going to put sine, I'm going to show you a little, -1 divided by -1. 0.8414. 709, yada, yada, yada. Okay. If you want to do, now you see, you probably didn't see what I did. You hit second, and then enter. It'll put that entry back in, and you can just go edit it. So I'm going to hit 0.5. And this pays off in larger problems. So if we keep going here, I'm just going to copy out of the book. You can see that it is getting closer and closer to 1. That's okay. We can do the same thing with the right-handed. You're actually going to get the same values. Okay, and you can see again 0 approaching 1. So we can say numerically now, because these match, the limit as x approaches 0 of f of x equals 1. You could, if you want, put sine x over x here. And we'll see that quite frequently. Okay, so that's numerical approach, graphical approach. Get the idea. Basically, we're coming closer and closer to some point. What's the value of that point? Okay, here's the formal definition. Okay, assume. You'll always have an assumption because you have to base your work on something. F of x is defined for all x in open interval containing c. That's some number c. It's an x value, but not necessarily c itself. So it contains c, but not necessarily c itself. It can have an open hole. We say the limit of f of x as x approaches c is L if the absolute value of f of x minus L becomes arbitrarily small
when x is any number sufficiently close to C. We're going to write it like this. The limit as x approaches C of f of x equals L. Okay. Yes, that's a touch confusing, but let's take a look at it. Sorry, bud. I'm on them. Okay, let's do an example. We know that, and I'm going to show you the definition here. The limit as x approaches 7 of 5. We know that if you graph that, the graph looks like this. And if this is 7, okay, the y value is always 5. So we know this is going to equal 5 by graphical interpretation. Okay, but we must show by definition f of x minus 5. Okay, that's L. So if you look at your definition, the limit is 5. So we must show that f of x minus 5 becomes arbitrarily small when x is sufficiently close to 7. Notice, though, that's true. We know that the value of f is always 5. 5 minus 5 is 0, which is about as arbitrarily small it gets. It's not necessary now to show that this is sufficiently close to 7. Okay, so because of the way this function behaves, we can show that for all x, not just 7, that this is true. Let's take a look at this function. Sorry. Okay, we got to show that f of x minus 13 becomes arbitrarily small when x is close to 4. So here's 13 is the limit, 4 is the x value. Okay, let's take, so f of x minus 13 is the absolute value, so f of x is 3x plus 1. If I do the math there, I get 3x minus 12, which I can actually take a 3 out because it's positive. Yeah, I can take that positive out of the absolute value. This shows that we can make f of x minus 13 small as x approaches 4. So if we can get this goes to 0, which is arbitrarily small, it implies that this is true. Okay, so that's using the definition. All right, let's look at this here. The limit as x approaches 9 of x minus 9 over root x minus 3. Notice if you plug it in, you get 0 over 0, which is something. We don't know what it is. But we go ahead and graph it. We're going to see that there's actually a hole here. All right, so graphically, as x approaches 9, from both directions, the function approaches 6. Okay? So we're looking at, as it goes x values, what happens to the y values. Numerically, you're going to see let's go left and right. 8.9, 8.99. Okay, you can see that this is going to 6. And then if you do this one, you would also see it's going to 6. So we can verify that this is true. Okay, they both have to go to 6. Sometimes we make it easy. If I plug 4 in here, x is 4, okay, then I have my answer. Okay, if the function is actually defined, here the function was undefined. So we had to do this numerical or graphical analysis, but if the function is defined, you have your answer. Okay, you have your answer. Let's look at another one. Somebody's been coloring. There. Okay. Let's look at the limit as x approaches 0 of sine pi over x. Again, the first thing you should notice, 0, plug it in, it's undefined. Okay? You're going to look at this thing graphically and notice that what it does is it kind of oscillates and then it just kind of does this number. But it doesn't settle. Same thing here. Comes in and it oscillates and oscillates, but it never does settle, and you can't really zoom in enough to get it to settle. So graphically, we can't see it. Okay. Numerically, So if we go from the left and the right, from the left, so you can see from the left we're going 0, positive, negative, positive, negative. It's not really settling. Okay, the same thing over here. Now you're probably wondering why we chose these numbers. You can choose any. I would just stick to the 0.1, 0.01, 0.001, etc. But this is going to show that it oscillates with these numbers. Again, we're getting a positive, negative, positive. Okay, so we say that the limit as x approaches 0 of sine pi over x does not exist, or dn. Feel free to write that on your homework, dne. We like shorthand. Okay. All right, a couple more examples. Let's look at one-sided limits. Let's say we take the limit as x approaches 0 of x over absolute value of x. Okay, does it exist? If we look at the graph, the graph simply looks like this. Okay, so obviously it's undefined at 0 because you can't divide by 0. But what happens here? Graphically, we see the limit as x approaches 1 from the left. That's this direction. Of f of x equals negative 1. We see the limit as x approaches 1 from the right is 1. Okay? These are not equal. Okay, so it has one-sided limits. So we could say that the limit, we could say this is true, and we can say this is true. From the left it's negative 1, and from the right it's 1, but we cannot say the limit as x approaches 1 overall. We have to say it does not exist, because it's coming to two different spots. 1, negative 1. If there's a split, we can't say there's an overall limit, but we can say there is a left-handed and a right-handed limit. Okay. Last thing, infinite limits. Let's consider something like f of x equals 1 minus x over 1 over x minus 2. If you graph it, we see at 2, the denominator is 0, so we know that there's going to be an asymptote here. Okay, so what do we say if sorry, that's not infinity, that should be 2. Okay, obviously the limit overall doesn't exist because they don't meet. These do not come together at a certain spot. But what if we approach 2 from the left? From the left, we're coming down, 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 down. Okay, so we're going to say it approaches negative infinity. The limit as x approaches 2 from the right is infinity. That applies in a lot of different situations. You have to look at the graph or look at it numerically. You can approach infinity. If you look at it numerically, these numbers will get small or bigger negatives. So smaller numbers will go into the negatives farther. These ones would go into the positives, and they'll get big fast. You know, you'll see jumps 100, 1,000, 10,000. All right. That should give you enough tools to work on 2.2. I think you've already written the work down, but I'll write it down anyways. And I have written it separately on the board. Two different days. I actually think, honestly, that this is B. Yeah, let's just write these down and then I'll figure it out for you. Yeah, this is actually part A and this is B. Okay, so, but you have the tools to do them all now, so you can get on it. Remember, it's not due until Thursday of next week on, let's see, what day would that be? The 18th, I believe? Yeah, do the 18th, so you have some time to look at it and complete it. I urge you, get this stuff down. Toodles.